Okay, so in this lecture, let's talk about subgroups generated by subsets of a group. So, subgroup generated by subsets. Let this be the precise title. Okay, so what are we exactly intending to do is that we start with a group. Okay, so G is a group we start with, and we choose an arbitrary subset of G. Okay, let A be a subset of G. We would obviously want A to be non-empty, but even if it's not, even if it's empty, then we'll find a way out. For yet, we are not imposing the fact whether A is empty or non-empty. Our target is to define or rather to acquire the smallest uh, subgroup of G which contains A. Okay, clear? So, so this is a statement or a definition to what we call a subgroup generated by A. So, subgroup generated by A is the smallest subgroup, or I should say smallest subgroup, which is uniquely determined, which is uniquely determined, containing A. Okay, so it's the unique smallest subgroup containing A, and we specifically denoted as this. Okay. Now, learners who have already studied group theory must be a bit familiar to this notation. Okay. But the matter of the fact is just stating that a subgroup generated by subsets is simply the smallest subgroup which contains A is not enough, because we need to give a certain structure, or rather I should say a certain form to such sets, so that we are able to construct such sets provided some subset A. Okay, so to that, we what we do is we actually sort of relate the concept of smallest subgroup to some relatable structure of a group. Okay, we will eventually notice what we are trying to do. um, we first start our discussion with a proposition which eventually speaks out the fact that we are calling this to be a subgroup. So it we need to at least justify for completeness of this lecture whether it's indeed a subgroup or not. Okay. So what we try to do is that let A be any non-empty collection, of subgroups of G of containing A. Or let me not specify the specified containing A at this point. Let me be on a general note. So let A be any non-empty collection of subgroups of G, then the intersection of all members of A is also a subgroup of G. Intersection of all members of A is a subgroup of G. Now, precisely what we are trying to do is that we are actually stating that any arbitrary intersection of any arbitrary family of subgroups is a subgroup. Let us try to prove this out. So, let us just resort to some notation. Mm, like obviously, if this is a non-empty collection of subgroups, suppose we write it like this. Okay. and let let A prime be the intersection of all the A's where A belong to this collection. Okay. Now clearly A prime is non-empty. A prime is non-empty as every subgroup will contain the identity element, right? So as one surely is in A prime. Okay. So we have to show that this is indeed a subgroup, and that's quite obvious to the fact. Let x y be in this intersection, but that indeed means that x and y in every A, are in A for all A in this. But that typically means that xy inverse is in A for all A in this. But that typically means that xy inverse is in the intersection. Right? So that implies subgroup of G. But there was nothing much to prove here. It was sort of easy. But using this, we can indeed, resort to the fact that this is indeed a subgroup because it is nothing but we can define this nothing to be an intersection. Reason being, we are concerned about the smallest subgroup which contains A. So if we take hold of all those subgroups which contain A and take their intersection, then we are done, right? Right. So definition, you can also consider this as a lemma as well. No, I don't think you should consider this. Yes, a definition will do because this is not something whose proof is required. So if A is a subset of a group G, G is a group, and okay, so we define, and this is quite intuitive, right? So this to be the intersection of all the subgroups H, okay, such that A is contained in H. Okay, clear. Now you can obviously come to the fact that this is indeed the smallest subgroup containing A, right? And this is simple set theoretic notion. There is nothing too precise in it. Okay. If A is in every subgroup H, then A is precisely in this. You can show a two-sided containment here. You can justify this on your own. That's an easy exercise. You just need to show two-sided containment. So this and this. And that's quite obvious. Okay. So now what if A is finite? Okay. So these are some notations which we regularly use, that if A is finite, let's say A is A1, A2, AN, then A is simply denoted as A1A, right? We do not use the brace for sets, to be precise. Also, one more thing which you can try and justify it out, that um, justify this will come out literally from the definition itself, that the smallest set containing A union B can be written as this. Okay, clear? Clear. Okay, now we are to construct of certain form to kind of make such sets constructible, to be precise. Okay, so our intention is to take hold of some form which is much easier to visualize, or at least much easier to to frame, in order to get hold of a set of a subgroup which is generated by some set. That's precisely what we want to do. Okay, so for that we need only one very simple definition. Okay, so let A bar be defined as A1 to the power epsilon 1, A2 to the power epsilon 2, and so on and so forth till An to the power epsilon n, where each AI is in capital A. Okay, epsilon I acquire only the values plus and minus 1, n is positive integers including 0, and all of these happens for all I. Okay. Okay. So it is simply now we are not at this moment also we are not concerned about the fact whether A is finite or infinite. What we are doing is we are only taking a finite number of elements from A, whether A being finite or infinite. If A is finite, there is nothing to do, right? It's very obvious. If A is infinite, we choose only finite number of elements and consider these expressions, sets, collection of these sort of expressions. Furthermore, one thing we impose on it is that A bar with A bar being 1 if A is empty. Okay. So now there is no question to ask whether A is empty or not empty. Clear? So what is A bar? So it's basically collection of all finite products. Okay? It's collection of all finite products, and these finite products, we call them words. Okay, we call them words. These are finite products of elements from clear. Now, one more thing, we are also not assured of the fact whether each of these AIs are distinct or not, and to be precise, we don't need that notion as well. That is, we are not concerned, about the, about whether each AI is distinct or not. Okay. And why is it so? We will see a bit later. Typically speaking, these AIs, AI to the power epsilon I form, these actually refer to A squared being written as A dot A. Clear? So even if suppose A1 and A2 are, are the same elements, so A1 epsilon 1 dot A2 epsilon 2 are nothing but A1 to the power epsilon 1 plus epsilon 2. So precisely, it doesn't matter whether they are different or same. Whatever. So our goal is to, or rather I should say, I claim that this collection A bar is nothing but the subgroup generated by A. Proof. Okay. How do we prove this? So obviously, our obvious procedure will be to show a two-sided inclusion. Now, is A bar empty? A bar is clearly non-empty, because even if A is empty, A bar is 1. A bar is the identity set, the set containing only 1. If A is non-empty, then A bar is obviously non-empty by its given structure. But we are imposing one more restriction on it, that even if A is empty, A bar is at least singleton 1. So there is no scope for A bar to be non-empty, right? So A bar is non-empty as if A is empty, A bar is 1, and if A is non-empty, then A bar is non-empty by its definition. So it's obvious. Okay. Now let A and B be elements from A bar. Then precisely they acquire the form which we have just written it down, right? So then A is of the form, say, A1 epsilon 1 till A n epsilon n, and let's say B is of the form B1, let's use delta 1 till say B m delta m. So these are finite products, right? So n need not be equal to m, and each epsilon 1 need not be equal to epsilon delta 1. Delta i's, epsilon i's need not be equal to delta i's. So there is no sort of equality necessary between them. That is precisely the fact. So what can I say about AB inverse? So AB inverse is A1 epsilon 1, so on and so forth till an epsilon n. And what is the inverse of this? We know that AB whole inverse is B inverse A inverse. So they just, so it starts with Bm to the power minus epsilon m. So it's Bn to the power minus delta m, sorry, not epsilon m. And here you have B1 to the power minus delta 1. Right? But indeed, this is an element of A bar, right? Therefore, A bar is a subgroup of G. So this is what we intended to prove first. That is indeed a subgroup of G. Because proving that, proving the equality of these two sets is quite easy. Whatever, it's indeed a subgroup. Now, we need to show that A is contained in A bar, but that's quite easy to show because, let A be in a capital. But then A can be done as A to the power 1, but A to the power 1 is an element of A bar by its structure. So that implies, A is contained in A bar, right? But if A is contained in A bar, then what we know about the subgroup generated by A is, so it's the smallest subgroup, it's the smallest subgroup containing A, right? So if it's the smallest subgroup containing A, it's the intersection. So if it's the smallest subgroup containing A, that means this should be contained in A bar, right? Because if it is not contained in A bar, as A bar contains A, so this does not remain the smallest subgroup containing A. This is one way of thinking this. Other way of thinking it out is that, this subgroup is the intersection of all the subgroups containing A, right? So A bar contains A. So A bar is also present in the intersection of all the subgroups which contain A. We know the intersection of each of the subgroups is contained in every subgroup. So this is contained in this. Okay, whatever way you can think of it, it's quite easy to get hold of this fact. Whatever. Got it? Okay. So yeah. Now we need to show the other side of the containment. Now how can we do that? Yeah, let me think a bit. Yeah, let's do it in this way. Observe that this contains elements of the form. Okay, every element of, or rather, let's not talk in this way. Okay, let me talk in this way. Let X be an element of A bar. Then X is of the form. So it's of the form this, right? Pi AI AI to the power epsilon I equals to 1 to n, such that for all AI is contained in A, epsilon I is equals to plus minus 1, right? By closure property of A, or I should say by closure property of this. So see, this contains A. So every element of A is contained in this set. This is a subgroup, right? So every element of this form should be contained in the subgroup generated by A. Okay? Because if A is in this, then A squared, A cubed, A to the power minus 2, all of these elements are in this by the closure property. Are you getting my point? Okay. I hope it's clear. So by the closure property of A, and since A is contained in this, every element of this form must be in the subgroup generated by A, which implies A bar is contained in this. So we have a two-sided containment, which implies that this must be equals to this. Okay, is it clear? Now if we consider G to be a additive group, then this A closure is typically the collection of all finite sums. Yeah, it's the collection of all finite sums of the elements in A. I guess this is clear. Okay. Now, so we have defined a structure to the subgroup generated by A, which is not only dependent on it being the smallest subgroup containing, right? Therefore, we have defined this to be of the form pi ai to the power alpha I is equals to 1 to n. Now we can, uh, bring together all the elements which denote the same element. I am being a bit, I'm fumbling a bit. So what I'm trying to say, suppose you have an element of this form. First thing first, you know, elements which are powers of A will obviously commute. Right? Powers of every element commutes because by the law of exponents. Right. So if the product is of suppose of this form, so it's A1 epsilon 1, A2 epsilon 2, A3 epsilon 3. Okay. And we get that A1 is equals to A3. So obviously I can bring it to here and bring this to here by commutativity because these are the, if elements of the, what I'm trying to say is that, see, if I have elements, which repeat, okay, or rather let me do it in this way. Let A be an abelian. I guess this will be better. Let A be abelian. Let G be an abelian. Okay. Then how can we define this? Now do we need the powers to be just plus minus 1? We can commute the elements by grouping them together and we can bring the elements which are the same together, right? So we can define it as pi I is equals to 1 to n ai to the power alpha I such that each of these alpha i's are elements from Z, no more just plus minus 1, and each of these ai are elements from E, right? I guess it's clear. Okay. Now this is pretty easy to observe. Now I was saying that we have a special case of this which is quite important, right? So okay, before moving on to that, let me consider an example. Okay. Now you guys know the definition of order of an element, right? So let me just quickly give the definition of order of an element. We will require this definition even while studying the very specific example in the very specific type of generated subgroups we are talking about. The definition is that, let G be a group and let X be an element from G. The order of X is the smallest positive integer, D, such that X to the power D is equals to 1. Clear? Okay. Now my question is that if I consider elements, which are of finite order, then will the subgroup generated by that element also be finite? That's my question. Okay. So my question is, if I have elements of finite order, then is it necessary for the subgroup generated by the elements, to be of finite order? Now order of a subgroup is simply its cardinality, to be of finite order. So that's precisely our question. Okay. So how can we answer this? Okay. So let's try and answer this out. What happens if the the group is abelian? What happens if the group is abelian? Observe that if if G is an abelian group, and A is say a finite set, let's say. So A is A1, A2, AK. It's a subset of G. Then observe that there exists exactly di distinct powers of each AI, provided that the order of AI is di. This happens for all I is equals to 1 to k. Okay, and if so happens, then obviously the cardinality of the subgroup generated by A will less than the product of each of these powers. So it's d1, d2 till dk. And why is it so? Because the total number of distinct products is at most d1 till dk. That's precisely the fact. So there is nothing too complicated about this. But is it in general true? That's my question. Is it true in general? Okay, but I claim that it's not true in general. That is, indeed, it's not true for abelian, non-abelian groups. Consider G to be the general linear group of matrices of dimension 2, real matrices of dimension 2. Consider two elements. Okay, let me use small a. So it's 0, 1. Yeah, sorry. We need to choose matrices. Small a is equals to 0, 1, 1, 0, and B is equals to 0, 2, 1 by 2, 0. Okay. Then observe that A square is 1. B square is also 1, I guess. Yeah, B square is also 1. What is AB? So it's 0 times 0 plus 1 times 1 by 2 is 1 by 2. 0 times 2, 1 times 0, 0. 1 times 0, 0 times 1 by 2, 0. 1 times 2. Yeah, so it's 2. Right, it's 2. Observe that the order of AB is infinite. So order of an element is said to be infinite if it does not have a finite order. So if order of AB is infinite, what does that directly mean? That means that the group generated by A and B is infinite. Right? But A and B are both of finite order. Right? Because if I consider this, then it will contain products of this order as well. Right? Elements of this order as well. I mean this form as well. Right? Okay. But A and B are individually of finite order. So it's not true in general, but if every element is of finite order, in case of a abelian group, then it's true. Okay, so yeah. Okay, let this lecture be up till this much. We just introduced the fact which we are trying to introduce, the concept of a cyclic group. Okay, so let A be a singleton set X. Then the group generated by A is simply denoted like this. It's called a cyclic subgroup of G. It's called a cyclic subgroup of G, and this subgroup is quite a very, very important subgroup. Okay, so we will discuss about cyclic groups in great details in the next lecture. So meet you guys in the next lecture.